And I'll post this lecture to YouTube today. I'll have to edit out the music at the beginning because they'll flag it. Let me add a page in here too. Let's leave it white. All right. What's today? 15, 16. All right, so today we're going to start talking about, and if at any point you can't hear me or something happens, just put a message in the chat, and I should be able to see it. So we're going to start today talking about chirality and stereoisomerism, and I wanted to also go back just for a second and talk about other types of isomers. So let's say I have a C4H10, so that can be a molecule that kind of looks like that, or it can look like that, right? Both of these are C4H10. Right? What is the relationship between these two? Like, what type of isomers are they? Anybody? They have the same molecular formula, but they have a different structure.
Are they constitutional isomers?
They are good, very good constitutional isomers. So same formula, different structure. And I'm gonna abbreviate this. So they are constitutional. I hate this word, by the way. Isomers. Right. So when we talk about isomerism, normally we think about constitutional isomers, but there's also another type of isomerism you may or may not, depending on how far you got in part one. I know for my class, we didn't necessarily get to this, but if I have, like, say, a Newman projection like this, and I have, come on, Russell, get your mind right. Here, right where I have the staggered projection, and then I have the same Newman projection, but I rotate 60 degrees around the carbon-carbon bond. Then I have the eclipsed conformation, right? These are also isomers. We call them rotational isomers. But there's also a type of stereoisomerism, right? So what a stereoisomer is, right? They have the same structure, but the 3D orientation is different. Right, so same structure, different 3D orientation. So these, the difference is the rotation around the carbon-carbon single bond. Is everybody familiar with what a Newman projection is?
Yeah.
Have you seen this?
Yeah.
Yeah. So this Newman projection is like for ethane. Let me just put the hydrogens in. Uh-oh, that's gonna get cut off. Hold up. Right. So that's all these are hydrogens, and they have different. The conformations have different energies. Let me erase that. So you won't think it's a radical, right? But this is based on looking at ethane. Squeeze that in there. Right, but taking this and basically looking down the carbon-carbon single bond that's here in the middle. Right, so it's almost like having one carbon facing you, kind of like it's kind of like looking down the insert for a roll of paper towels, right? If you look through the hole on one end, you can see out the other end. If you turn this molecule so that this carbon, right, either carbon, but I'm going to pick this one, like so that this carbon is facing you, then you see down to the other carbon. And so that's what these Newman projections represent, like looking down a carbon-carbon single bond, right? So that's a type of stereoisomer, and that gets us into the definition of stereoisomers, which is two molecules that have the same structure, but they have a different 3D orientation. So how does that lead us to any questions before I move on? I don't want to rush because I know I'm writing and talking a lot. So just let me know. This is a discussion more than it is a lecture. So if you have a question, just say something.
Yes, sir. So does that mean that constitutional isomers are supposed to be synonymous to stereoisomers?
No, constitutional isomers are different because they have actually two separate structures. You see how these two structures are different? Like they have totally different structures. So they're not stereoisomers at all.
Okay, understood.
Stereoisomers will have the same structure, but they'll have a different orientation in space. I'm gonna show you when we in the next little section, we'll talk about chiral. We're gonna talk about chirality. Let me put another page in here.
Dr. Rusko,
Yes, go ahead.
you said the assignment folder was visible now?
Yeah, it should be open now in Blackboard. You should be able to see it.
Okay.
All right. So this is a type of stereoisomers. I don't know how far you got in organic one, but if y'all got to chairs and boats, all right. So this is one chair. Let me just put the methyl group here. And then if I do a chair flip, not sure if y'all got to that or not. If you didn't, it's fine. I'm happy to explain it. I know I didn't cover it in my class because we ran out of time. Right, so with this chair, this is a cyclohexane ring. This is the favorite conformation for it. And the substituent, a methyl group, in this case is what we call axial because it's pointed up. And when it's axial, it costs energy to be that way. And so these rings can contort through what's called conformational mobility. And that axial substituent, if the ring flips, it goes to this conformation or to this position, which is what we call equatorial. Right? So axial and equatorial, these are also stereoisomers because they have a different 3D orientation, although they have the same structure. You can see here a little bit more clearly where you have the methyl group pointed up in one, and then the other chair, you have the methyl group pointed horizontally or on an equatorial position. All right, so how does that lead into what we're going to be talking about for the next week or so, dealing with chirality? So now let me segue into that. Change my pen. You have to excuse my handwriting. I hate to use a stylus because they always screw up. And yeah, this was my worst subject in elementary school, handwriting. right? So how this ties into chirality is that there's another type of stereoisomer that's possible. And before I show you all the nuts and bolts of that, I'm just going to show you a basic tetrahedral carbon. All right, so here's a carbon, and you've all seen this depiction of carbon before, I'm sure. So that's a tetrahedral, right? A tetrahedral depiction of carbon. And you already know the bond order. It's got 4 groups around it because it can't have more than 4 groups. And it has a bond angle of 109.5, right? Now, if I would have just put hydrogens around this, that's not chiral, right? But if I took that same carbon, and I'm gonna cheat and copy this, come on. If I took that same carbon and I swapped out 3 of the groups, and I put some different groups in, let's say a OH, NH2, and a CH3. Now, this carbon becomes what we call a chiral center. Right, is what we call a chiral center now, or another term that you'll hear me throw around that's equivalent to chiral center is a stereo center. Right, the stereo part is based on the fact that it's based on now it has handedness and it has a 3D orientation, right? Whereas the tetrahedral up top, because all the groups are the same, there's no handedness, right? There's no chirality. The minute you take a carbon, or you can see this same phenomenon with nitrogen, with sulfur, with silicon, other atoms like that. The minute you put those 4 different groups around it, it becomes chiral, right? Can somebody who watched the video tell me what the criteria are for chirality? So I can squeeze it over here.
For a chiral center, it needs to have 4. It needs to have 4 different groups. It needs to be sp3 hybridized. Damn, I forgot the other. Let me see.
That's that's okay. It needs to be sp3 hybridized. It cannot be symmetrical.
It says something about handedness.
Yeah, so this contributes to the handedness, right? The 4 different substituents, the fact that it's sp3 hybridized, is non-symmetrical, and the big one, which is where we're going to take this, is that it's non-superimposable. I got to make more room for that because I need to write that whole word out. On its mirror image. That's the big thing that leads us, that's going to lead us into another concept of stereoisomer, or another type of stereoisomer. Right? So you have 4 criteria that make an atom a chiral center. It's got to have 4 different things around it. It's got to be, and if you look at the first 2, they play off of one another, right? Because if a carbon or some atom is sp3 hybridized, that means it's going to have 4 groups. Just like if it's sp2 hybridized, it's going to have 3 groups attached to it. And if it's sp hybridized, it's going to have 2 groups attached to it, right? Y'all remember that from part 1? Recall that from part 1 when you talk about hybridization?
Yeah.
All right. So the 4 substituents and the sp3 hybridization go hand in hand. The fact that you got 4 different substituents also means that the symmetry is not going to have any symmetry, right? So as long as there are not 2 or more substituents that are identical, then it's going to be non-symmetrical. And then the other part, the most important part is that it's non-superimposable on its mirror image. These criteria make a molecule or atom chiral. And if you have a chiral atom within a molecule, then it makes the whole molecule chiral. We're going to see that later. All right. So this leads us to a whole nother, that's bad, ain't it? It leads us to another type of stereoisomer, which is going to be based on that last criteria, that it's a non-superimposable on its mirror image. So you can have a chiral center like this. Let me copy it again. That's why I love this program. Come on. I don't like that part though. Where are you? Copy. Paste it down here. Didn't mean to get all that. Never mind. I'll just redraw it because that's stressing me out. All right. So let me just redraw this carbon. Right. And if you let me make a point right here too. If you notice, like I have the CH3 on a wedge, it's on like a thick darkened line. That's on purpose. That means what that indicates is that CH3 is coming out of the screen at you, right? And then the hydrogen being on a dashed line, that means it's going back into the page, right? So down here, let me fix that up so it'll look a little neater, right? I have the hydrogen going back into the page, and then I have the CH3 or the methyl group coming out of the page, coming out at you, right? And if you have a model, if you built a tetrahedron, and you could see exactly what I mean, right? Like one of the groups is going to be coming out, one of them is going to be going back into the page, one's going to be pointed up vertically, and then one is going to be on a horizontal line, like the NH2 that's shown. I'm going to shrink that down some so I can actually put in the mirror image. All right, so that's that. And then, so the mirror image of this, I'm going to draw like this. So this is looking at itself in a mirror, just like if you were looking at yourself in the mirror. What's the first thing that it is going to see?
NH2.
The NH2. Good. So I'm going to write that like this. That's still on a horizontal line. All right. And then here's the same carbon. The OH is still vertical. Nothing changes there. And then the methyl is going to be here. And then the hydrogen here. Let me fix that up. Right? Questions about that? So that's the mirror image. And I'm going to explain what superimposable means. And then we're going to look at a couple of other types of stereoisomers. And then we're going to jump on that handout. So the mirror, these two are what we call enantiomers. Right? They are, which means that they are non-superimposable mirror images. That's the definition of an enantiomer. Non-superimposable mirror images. Right? Now, what is the term? What does it mean when I say superimposable? It means that if I took the mirror image and I flipped it over to triangle lay it on top of the original image. So this is, we're gonna call this original. Let me move that down. I don't want to put it on that line. So that's my original image, and this is the mirror image, right? So if I took the mirror image and I tried to lay it on top of the original so that all the atoms matched up, right? How would you do that? Anybody? What would you do to do that? To get the NH2s aligned, to get the OH aligned, to try and get the CH3 and the H aligned? What would you do if I ask you to superimpose it?
Wouldn't you have to like physically change that molecule? So you would have to flip the NH2 and the CH3?
Yeah, you need to rotate it in space, right?
Yeah.
Is that what you mean? Yeah. So I like to think about this, and been teaching this forever. I talk about it the same way. It's like if I put a spatula underneath the mirror image and flipped it over like a pancake. That's the idea of trying to superimpose them. So if I'm going to draw the mirror image in a different color just to make it make sense. So if I took the mirror image and I rotated it over or flipped it over this way, right? So that the CH3 would be facing the same way as the CH3 over here, and the H would be facing the same way, and NH2, all the atoms would be facing the same way. If I flipped it over, it would look like this. So this is OH, this is C, this is NH2, right? But the methyl and the hydrogen are going to switch places. Can y'all see that? Because when I turn it over, whatever is wedged is going to become dashed, and whatever is dashed is going to become wedged. So this is the right. That's the mirror, but it's now flipped over. Any questions about that, or any confusion?
Could you repeat that again? You said what do you mean, like whatever is wedged becomes, can you repeat that again?
Yeah, I need to fix that too because I screwed that up. Yeah. So what if you see how the CH3 on the other side is wedged on the mirror image?
Mm-hmm.
If I rotated that around the whole molecule, right, that CH3 is going to end up pointing back here.
Oh, where the hydrogen was.
Mm-hmm. And the hydrogen is going to end up here. Because I'm turning the whole thing over. I'm not just moving one part of it. I'm rotating the whole thing around in space.
Okay, got it.
Does that make sense?
Mm-hmm. Thank you.
Yeah. Another way to think about it, if the spatula analogy doesn't work, is to put an axis here. Right, you can put an axis through it here and just rotate around that axis. Right? Either way, you're going to flip it over. This works great for tetrahedrals, not so much for Lewis and line structures and skeletal structures, but I'm just trying to get the concept to you first before we start looking at some of these examples. All right, so that's an example of enantiomers, and enantiomers are a consequence of having a chiral center present, and the chiral center arises from having 4 different substituents, that being sp3 hybridized, non-symmetrical, and all of those 3 means that the mirror image will be non-superimposable. Any questions on that before we move on to anything else?
Yeah, I had one. So just to basically clarify, when you're rotating a non-superimposable enantiomer, you're gonna get what you basically just said for that green. That's just okay. Just clarify.
Yeah. So this is, remember, I'm rotating this image right here. Right. So I'm turning that all the way around in space, and the CH3, you can kind of, if you think about it, like you're turning it on, let's say we're turning it on the axis. So this is everything on that bottom, all the groups on the bottom, right? Let me highlight them. So here, here, and here, all those groups are gonna move around like on a carousel.
Yeah, I seen it better now. I just wanted to clarify it was just for these particular stereoisomers.
And you can do this with any set of enantiomers, but it's a little different when you have more atoms, right? When you have a skeletal form that has multiple chiral centers in it, then it becomes a little bit more laborious to do it. But the idea is that when you flip it over, everything inverts. So everything that's wedged becomes dashed, and everything that's dashed becomes wedged, right? And you can see that down here in the flipped over mirror image. The CH3 was on a dash in the mirror up top, and when I flipped it over, now it's on a wedge right here, right? And then the H was on a dash, and now it's on a wedge. I think I said the CH3 part backwards. It's on a wedge up top, and down in the flipped over image is on the dash. All right, is this making sense? Yes, no, maybe?
Yes.
Yes.
Somewhat. All right.
What
Go
would be
ahead.
the purpose of wanting to even rotate such
Well,
things?
it's not really necessary, but right now the purpose is to show you that you can't superimpose them. Right, and I'm gonna show. Let me just copy. Let me see if I can copy this image right here, and I'm gonna show you what I mean by that. Right, because one of the criteria is that you should not be able to superimpose the mirror image onto the original image. Are you following? So if I paste that down here, let me paste it, paste, and I can. You see that? So if I took this and tried to lay it on top of this, do you see how the CH3 and the H doesn't match?
Yes.
So that's why I'm talking about it now. But in reality, it's a given. If you have an enantiomer, if you have two enantiomers, it's a given that you can't superimpose them, right? But I'm trying to get the concept out, so when we start seeing this with other types of examples, that's not something that's going to trip you up. Right? Can everybody see that? How if I tried to lay this on top of the other one, the black one on top of the green one, the black is the original image, the green is the mirror image. You see how the CH3s and H's are off, even though the OH and the NH2 line up. I can't line everything up. And if I can't line all the atoms up, then that means that's not a chiral. That means that it is a chiral center. If I can line them all up, then it's not a chiral center. But this is what I mean by non-superimposed.
Dr. Russell, can you repeat that again? You said if you can line them up, what did you say?
Then it's not chiral. Right.
Okay.
But if I cannot line them up, which is what it means to be non-superimposable, then it is chiral. And you can see that here. You can see how the groups don't match. The NH2 matches, the OHs match, but then the methyl and the hydrogen don't. So that means that this is indeed a chiral center, and these two are indeed enantiomers. All right, questions? Any questions about that? I'm gonna move this now because I want y'all to be confused when you download these notes. Or should I leave it?
Delete.
All right. Any questions about anything?
Are you posting this recording on Blackboard?
Let me actually move it up. It'll be on YouTube,
Okay.
on the channel. I'm just gonna highlight this just to make it make sense. Yeah, it'll be on the YouTube channel. Let me move this around. That's the original. All right. Any other questions about anything so far? So these are what we call enantiomers. And then we have another set of stereoisomers that we can talk about. Let me add a page. So this is one set of stereoisomers that's based on the presence of a chiral center. And then we also have another type of stereoisomer that we can talk about, which is diastereomers. And then we're going to get into that handout. Right? In order for a diastereomer to exist, you need a minimum of 2 chiral centers. So you got to have at least 2 chiral centers in order for this type of stereoisomer to exist. All right. And so let me give you an example. And a lot of times when we talk about diastereomers, you'll see these written as Fisher projections, which we're going to talk about, or sometimes, and just as a to keep it basic, you'll see it written as a skeletal form. All right, and if we look at the molecule itself, you can see that it has 2 chiral centers, but let's prove it. So is this a chiral center? Yes or no? And how would you know? Again, think about the criteria for chirality. sp3 hybridized, 4 different substituents, right? Non-symmetrical, and the final one is not being superimposable on the mirror image. So would that, you think that carbon right there would be a chiral center?
Yes.
Yes.
Yes. You can see immediately, let me change that up, that it has one thing bonded to it here, a CH3 here, and then a carbon here. And then on the dash, what was not shown is hydrogen, right? That's very important. Anytime you don't see another atom on that carbon and it has a wedge or a dash, the other atom is always assumed to be hydrogen, right? And it's pointed back. All right, just like on the other side, on the wedge, I have an OH group. Let me make that neater slightly, right? So what does that mean? What's on the wedge if the OH is on the dash and no other atom is shown?
It would be the hydrogen.
Understood that there's a hydrogen there, and it is on a wedge. It's always going to take the opposite position of what's there. So if what's on that atom is dashed, then the hydrogen is going to be wedged. If what's on the atom is wedged, like the NH2, then the hydrogen is going to be dashed, right? And so again, if you look on this side, you can see that this is also a chiral center, right? It's got 4 different groups attached to it. It has the OH, it has hydrogen, has a CH3 here, and it has this carbon here in common with the other side. But that's still a point of difference. And that matters when we start talking about configuration, which we're gonna jump into before we are done. And then we'll come back to that, and then we'll start working through some more of these examples on Wednesday. But so that part is settled, right? We do have both of those are chiral centers, right? So that part is settled. So a diastereomer is not a mirror image, right? It's not a mirror image. It is, but it's still a stereoisomer, right? So the best way to explain that is can generate a diastereomer by altering one of the two stereocenters here that's present, or one stereocenter out of the multiple stereocenters that are present. So let me talk about that. So the diastereomer of this, I'm going to leave this how it is, and then I'm going to alter the OH. And I need to fix that little wedge. All right, are y'all following that? So notice this stayed the same. Right, and now this is different. Let me not say different. Let me say inverted. Right, when you compare it to the original image, which is up top. All right. So the original, and this is a 1 diastereomer. Questions about that? So I left one stereocenter the same, I changed one. That's what a dot, so it's not a mirror image, because in the mirror image, both of them would change. Am I right about that? Because in the mirror image, everything gets reversed. So if it was a mirror image, then they both would change. But the fact that only one changed means that this is what you call a diastereomer and not an enantiomer. So it's another type of stereoisomer. All right, questions. All right, so another piece of information that we can get from this is the fact that you have two stereoisomers present, or two chiral centers present. And what that means is that there's a way to determine how many actual stereoisomers are possible, right? So we can determine that with a little formula. So I'm going to write that here, number of stereoisomers. And then we're going to figure out how many we should get for this, and then we're going to draw the other ones. Right? A very simple formula, 2 to the n, where n is the number of chiral centers. All right, so n is going to be the number of stereocenters. Are y'all following that? If not, say something.
Yes.
Okay. So how many stereocenters did we say are present here? How many chiral centers in the first the original?
There's 2.
2, right? So for that molecule, if I do 2 to the n, there are 4 possible stereoisomers for this molecule. Are y'all following that?
Yes.
We have 2 shown right here. Is that right?
Yeah.
So that means that there are 2 more that are possible. Yes.
Yes.
Yep.
All right. So look at the diastereomer that I did, the first one that I did, the blue in blue, right? What else can I do to the top one to generate another stereoisomer?
Invert the left side.
Invert the NH2. Great. Man, it's going to be a good semester. I can already tell. So I'm going to do this. Zoom in so I can get my dashes straight. I want my stuff looking sloppy on YouTube. We got to represent. Is that right? Like that. And then leave this side how it is. Is that right? No. That's not wedged. It's dashed. Like this.
Well, no, I thought you said that they both couldn't be like that. Why wouldn't you keep the H the same?
Because the OH in the original, look at the original. The OH is dashed.
Got it.
Mm-hmm. So in the original, the OH is dashed, is that right? And I inverted the NH2.
Got it. I was looking at the wrong one. I was
That's okay. Now, what else can I do?
Invert both of them.
Okay, so that one would be if I took the top and if I inverted both, what would that be compared to the original image?
Oh, a mirror.
A mirror image, very good. Let me pick a different color. So I could also have, that has a mirror image, and we know that, right? So that's gonna be NH2, and this is gonna be OH, is that right? And that will account for our other two stereoisomers. Yes, no?
Yes.
So we have a total of 4, is that right? And if we look at these, can you see the relationship between these two right here? What's the relationship between those two? Let me see if you can pick that up.
Mirror.
They're mirror images, aren't they? Because both groups are opposite in each one of those. Compared to the original image, they are diastereomers, but compared to each other, they are actually enatiomers, right? So you can have both. And then what about the relationship between, let me get a different color. Yeah, that'll work. These, what do you think?
Those are also mirrored.
They're also mirror images, right? But compared to the other ones that I just showed that have the blue highlight between them, they're diastereomers. Are y'all following that? So you can have, actually, you can see both types of stereoisomers. When you start having multiple chiral centers, then it's possible to see both types of stereoisomers. Now let me make this make sense, right? And make it relevant to what we're pursuing. So let me find what I told you. Is my screen still visible? Can you see my browser?
Yes.
Yeah.
Okay, perfect. Let me pull up this molecule. I'm gonna tie all this together in one image. If my Wi-Fi wasn't so cheap, it'd already be up. Come on, man. All right, let me see if I can pull this up. And then we'll close out with this, because I want this to kind of sink in and resonate. Can y'all see this molecule right here, paclitaxel?
Yeah.
Right. This is Taxol, and it's extracted from the bark of the Pacific yew tree. It's one of the first lines of defense against like several different types of cancer. If you notice, let me see if I can cut this. Let me put it so I can put it in our, come on. Right, if you notice in tax chiral centers, come on now. Right. Let me I'm gonna add another page and see if I can paste that into here. Right, and I just want to make this relevant to what we're talking about, because this stuff is not like some pie in the sky, like esoteric lunacy. Like this is real. It has really serious implications and application. Right, so if you look at that Taxol, if you notice here, how many stereo centers are here? 1, 2, 3, 4. Oh, not that one. That's SP2. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 chiral centers. 11 chiral centers. Somebody put that in your calculator and tell me how many stereoisomers are possible. All right, and again, this is a cancer treatment. It's one of the first lines of defense. Before my wife passed, she actually took this first before she took anything else. My mom had to take it when she had breast cancer. So it's a very powerful drug. And again, it's derived from a natural source, but in order to get enough of it to treat a cancer patient, you have to cut down like 1 million yew trees, and they take 100 years to grow back. So somebody had to come up with a way to make it. So you had really two groups that were in competition to synthesize it. How many stereoisomers are possible for Taxol? Anybody put it in your phone yet? Put that 5G to work.
2048.
2048 possible stereoisomers. You know how many out of those 2048 work against cancer and work to fit the exact receptor that needs to be touched in order to cause apoptosis? One, this one. All right. So what that means is that all of these chiral centers have to be perfect. This is the only one that works against cancer cells, right? Because that chirality causes this to be able to fit into the right receptors. And when it fits into the right receptors, then it's going to cause cell death like it's supposed to. The pathway to cell death might be different for different types of drugs, but everything is based around the fact that these chiral centers give this molecule a shape. And the fact that it has a shape means it fits into a specific receptor within the cell and it's able to do its job. If one of these stereo centers is off, then this is ineffective, completely ineffective, or it might kill you, right? Because obviously it's chemotherapy, so there are some side effects. But what I'm saying is it may cause more harm than the actual cancer that's in the body, if one of these stereo centers is off, right? So that's why when we talk about chirality and stereoisomerism and enantiomers and diastereomers, then it's not just like some stuff we just making up or pulling out of the sky. It's like real legitimate science, and we need that. We need to understand that, and that'll help us understand like other things like this, right? How certain drugs fit into certain receptors, how certain receptors have a shape. And if the drug has stereo centers that are not the right configuration, which we're going to talk about Wednesday, then they don't fit into the receptor and they're ineffective. And they might cause damage to other places where they shouldn't. And I know that's kind of when we talk about like chemotherapy, that's kind of like understood because it does affect other things. But the main purpose to actually kill the cancer that's in the body is only served if these stereo centers are in their proper configuration, right? So you got 2,048 possible stereoisomers, but only one that works. So when this is synthesized, it has to be all these stereo centers have to have what the configurations that are shown. Otherwise, it's a wrap. All right. So go ahead.
So how exactly did one of my colleagues take 11 and get 2028?
Say that again.
what was the math that was done to get 11 to 2048?
Oh, it's two. Remember, the number of stereoisomers is 2 to the n. So that'd be 2 to the 11.
Okay, understood.
Yeah, great question. All right, we got to stop because I could talk about this stuff all day, as you can tell. But we'll come back. And well, go ahead. I see a hand up. Was it already up?
I do have a question.
Okay, go ahead.